Welcome to the deep dive. If you're a Java developer aiming for that senior role, it's not just about the latest frameworks. It's really about, well, understanding those core concepts, the ones that seem simple, but have incredible depth and can really trip you up in an interview. Today, we're diving deep into one of those, Java generics.
Exactly. And our mission today, well, it's to equip you with more than just the textbook answers. We want you to feel confident discussing real-world scenarios, the advanced stuff, turning these complex ideas into, clear, articulate answers, the kind that senior interviewers are actually listening for.
Right. Think of generics like maybe an adjustable wrench in your Java toolkit. That's kind of a good analogy. A powerful tool that adapts, helps you build robust, flexible code. So we're going to open up that toolbox. We'll look at generic classes, methods, and those really crucial type bounds.
Okay, so let's unpack generic classes first. At its simplest, it's a class, but with one or more type parameters, right? Like leaving a blank space for the type. That's a good way to put it. A classic example you'll see everywhere is something like entry of k, comma, v. See, k and v aren't concrete types yet. They're just placeholders. And within that class definition, you use k and v as if they were real types. For instance, variables, maybe method parameters, return values.
Ah, okay. So it's a template.
Exactly. A template for a customizable container. You define the structure, but you delay specifying what it holds.
And then when you actually, create an instance, you fill in those blanks. You'd say entry of string, comma, integer. And boom, the compiler knows it's a string key integer value. So get key returns string, get value returns integer. It just clicks into place.
Precisely. And that leads us straight to a key point, a common interview question, actually. You cannot use primitive types. So entry a string, comma, int, nope, invalid.
Ah, right.
Generics only work with objects. So you absolutely must use the wrapper classes, like integer instead of int. Getting that wrong, well, it signals a misunderstanding of Java's type system.
And then there's the diamond operator, that less than greater than thing. That came in Java 7, right? It cleans things up a bit. Instead of entry of string, comma, integer, entry equals new entry of string, comma, integer, open parent, Fred, comma, 42, close parent, semicolon. Tedious. You could just write entry of string, comma, integer, entry equals new, entry diamond operator, open parent, Fred, comma, 42, close parent, semicolon. Much cleaner.
It is. And mentioning the diamond operator shows you're up to date. The compiler infers the type string and integer from the variable declaration. Less typing, same type safety. So yeah, think customizable containers. You label the box for what goes inside, and a little mnemonic maybe. Generic equals general template, specific equals substituted types.
Oh, good mnemonic.
And we should also briefly touch on type erasure. This is a big one. At runtime, that specific type information, the string and integer in our entry, it's mostly gone. In the bytecode, entry of string, comma, integer just becomes entry.
Whoa, okay, so the safety check is purely at compile time.
Largely, yes. The compiler uses the generic info, then erases it. Understanding this is critical. Not knowing about type erasure can lead to some real red flag answers in interviews. Like, for instance, using raw types. Just writing array list instead of array list of string.
Oh yeah, don't do that.
Exactly. You lose all the compile time safety. Always specify the generic types. It's why they exist.
Okay, so generic classes are our customizable containers.
Yeah.
Got it. But what about actions? Like methods that need to work on different types are adjustable tools. That's generic methods, right? And they can even be in regular non-generic classes.
Yep, exactly. The arrays utility class is full of them. Take a simple swap method. You could define it as public static generic t void swap t array, comma int I, comma int j. See that t? That declares a type parameter just for this method. It means this method can swap elements in any kind of object array. String array, integer array, employee array, whatever.
They're flexible.
Super flexible and still type safe. When you call it, say arrays.swap with friends indices 0 and 1, assuming friends is a string array.
The compiler figures out t must be string.
Right. That's type inference in action. It looks at the arguments you pass in.
But what about that syntax? You said public static generic t void swap. That order matters, doesn't it?
Oh, absolutely. That's a classic interview check. The type parameter declaration, the T, always comes after the modifiers like public static, but before the return type, void in this case.
Got it. Modifiers, then type parameter, then return type.
Exactly. There's even a little mnemonic for it. Type parameter before return type, TBR.
TBR, okay, I can remember that.
Putting the T after the return type is a common mistake, a definite red flag.
Okay. You mentioned type inference, but sometimes you've seen people write arrays.stringswap with the type explicitly. Why?
Good question. Usually, inference works fine. But sometimes, maybe with complex generic setups, the compiler might get confused, or the error messages if something is wrong aren't very clear. Specifying the type explicitly, like arrays.stringswap, forces the compiler's hand. It says, hey, I expect T to be string here, which can lead to much better error messages if you've made a mistake elsewhere.
Ah, okay, so it's like giving the compiler a stronger hint, or for debugging.
Pretty much. So generic methods are adjustable tools. One method handles multiple types safely. Just remember TBR for the syntax. And another quick point, static generic methods, like our swap example, can't use the type parameters of the class they might be in if it were a generic class. They only work with their own T.
Right, because static belongs to the class, not an instance. Makes sense. Okay, so we have flexible classes, flexible methods. But what if the flexibility needs limits? Like the type parameter isn't just any type. It has to have certain capabilities, like job requirements.
Exactly. That's precisely what type bounds are for. You're putting constraints on the types that can be used. Let's say you want a method to close a bunch of things, but only things that can be closed, things that implement auto-closable. You'd write the method signature like public static generic T extends auto-closable void, close it, all array list of T elements throws exception.
Okay, T extends auto-closable, so that extends keyword is the key here.
It is. It means T must be a subtype of auto-closable. It could be auto-closable itself or any class that implements it, like printstream. This guarantees that inside the method, calling ln.close is safe. The compiler knows that method exists.
So you couldn't pass an array list of string to that method.
Correct, because string doesn't extend or implement auto-closable. Compile time error. That's the safety net.
Now here's something that always felt a bit weird to me. That extends keyword. It's used for interfaces too, not implements.
Yeah, that catches people out. In the context of type bounds, extends means is a subtype of or conforms to. It applies whether the bound is a class or an interface. They just reused the extends keyword for simplicity rather than adding implements specifically for bounds. So T extends runnable is perfectly valid for an interface bound.
Okay, extends means is a subtype of for both classes and interfaces in bounds.
Got it. And this distinction is crucial when we talk about a really important senior level concept, array covariance versus generic invariance.
Ah, yes. This one comes up a lot.
It does. Think about arrays first. Java arrays are covariant. This means if printstream is a subtype of auto-closable, then printstream array is considered a subtype of auto-closable array.
Okay, so you could pass a printstream array to a method expecting an auto-closable array.
You could.
Yeah.
But it opens the door to potential runtime errors.
Yeah.
You could try to put something else that's auto-closable but not a printstream into that printstream array, leading to an array store exception at runtime.
Ouch.
But generic collections, like ArrayList, are invariant. An ArrayList of printstream is not considered a subtype of ArrayList of auto-closable.
Why the difference?
For safety. If generics were covariant like arrays, you could assign an ArrayList of printstream to an ArrayList of auto-closable variable, and then accidentally try to add, say, a socket, which is also auto-closable to it. That would break the promise that the list only contains printstream objects.
Compile time safety versus potential runtime errors.
Exactly. Generics prioritize compile time safety, and that's why our closeAll method needs the type-bound T extends auto-closable when working with an array list of T. It enforces the necessary capability at compile time, working around the invariance.
That clarifies a lot. So the bound enforces the contract. What if you need multiple contracts? Multiple job requirements?
You can do that too. Multiple bounds. Let's say T needs to be runnable and auto-closable. You'd write T extends runnable and auto-closable. The N symbol means and. So T has to satisfy both conditions.
Okay, extends runnable and auto-closable. Makes sense.
Okay.
Any rules there?
One very strict rule. If one of your bounds is a class, and you can only extend one class, that class must come first in the list. So it's T extends my class in interface 1 and interface 2, never T extends interface 1 in my class.
Class first, interfaces after.
Precisely, a good mnemonic. Class first, interfaces after. And watch out for common interview mistakes here. Confusing type bounds with wildcards, they're related but different. And, as we hammered home, not grasping invariance, and always use extends for bounds, never implements.
Okay, we've hit the core pieces. Classes, methods, bounds. But let's dig into some of those trickier nuances that really show senior level understanding. We mentioned type erasure briefly. Can't we revisit why that prevents creating generic arrays like new entry of string, comma, integer array of 10?
Sure. It goes back to the fact that the string and integer type information isn't fully present at runtime. The JVM needs to know the exact component type to create an array, mainly for those runtime checks we talked about, like preventing an array store exception. Since the specific types string, integer are erased, the JVM doesn't have what it needs to create entry of string, comma, integer array. It only sees entry array.
So it can't enforce the type at runtime for array storage.
Exactly. That's why the language forbids it. The standard workaround, and the generally better practice anyway, is to use a generic collection, like array list of entry of string, comma, integer. The collection manages the underlying array, usually an object array internally, and uses casts, which are safe because of the compile time checks.
Makes sense. A consequence of prioritizing compile time safety and backward compatibility. What about static members? Why can't a static field or method use the class's type parameter, like t in entry of k, comma, v?
Because static members belong to the class itself, not to any particular instance of the class. The type parameters k and v are only defined when you create an instance, like new entry of string, comma, integer. A static member exists before any instances, so it can't possibly know what k and v will be for some future object.
Right. Instance data versus class data.
Correct. If you need a static method to be generic, like our swap example, it has to declare its own type parameter, like t.
Okay. And you mentioned it before, but let's re-emphasize the covariance versus invariance thing. It seems really critical.
It absolutely is. It's probably one of the most common areas interviewers probe for deep understanding. Just remember, arrays are covariant. String array is an object array, which allows flexibility but risks runtime array store exception. Generic collections are invariant. Array list of string is not an array list of object, to guarantee compile time type safety. Understanding why this difference exists is key.
And a quick practical note, performance. Using integer instead of int involves boxing on boxing, right? Any real impact?
There is an overhead, yes. The conversion between primitives and their wrapper objects takes time. In most typical enterprise applications, this overhead is negligible thanks to JVM optimizations. But in highly performance-sensitive code like numerical computing or low-latency systems, it could be a factor to consider. It's good awareness to have.
Good point. And just to hammer it home one last time, raw types.
The ultimate anti-pattern. Using array list instead of array list of string throws away all the benefits of generics. You lose compile time safety, you get compiler warnings, which you should never ignore, and you risk runtime class cast exceptions.
So just
Don't. Please don't. Always specify the generic types, and use the diamond operator in constructors to keep the code clean and readable. That's best practice. And remember that explicit type specification for method calls, arrays.stringswap, can be your friend when inference gets tricky or errors are obscure.
excellent. Okay, let's switch gears slightly. Imagine you, the listener, are sitting in that interview chair. Let's run through a couple of typical questions.
All right, scenario time. First question. Why can't you create arrays of generic types directly, like new list string 10, and what's the standard workaround?
Okay, thinking. The answer involves type erasure, right?
Exactly. You'd explain that due to type erasure, the specific type information, string in this case, isn't available at runtime, which the JVM needs to create a typed array safely. The workaround is to use a generic collection, like array list of string, which handles the underlying storage safely.
Good. Okay. Second question, hitting that core concept again. Explain why array list of string is not a subtype of array list of object, but string array is a subtype of object array.
This is the invariance versus covariance question, you'd explain. String array is a subtype of object array because arrays are covariant in Java. This allows assignment flexibility but risks runtime array store exception if you misuse it. Array list of string, however, is not a subtype of array list of object. Generic collections are invariant. This design choice prioritizes compile time type safety, preventing you from adding, say, an integer to a list that's supposed to only hold strings, which could happen if generics were covariant.
Perfect. And a general tip when answering these, be precise. Use the terms type erasure, covariance, invariance. If you stumble, try to explain the implications why it matters for type safety rather than just stopping. And definitely avoid saying things like, it just works that way, or I read it somewhere. Show your reasoning.
Absolutely. Show, don't just tell.
What we've really dug deep today, Java generics, covering generic classes, methods, and those really important type bounds, from the basics to the gotchas.
Yeah, we went from customizable containers and adjustable tools right through to defining those specific job requirements for types. The main takeaway. Generics are fundamental for writing robust, reusable, and crucially, type-safe Java code. Getting comfortable with these concepts isn't just about passing interviews, it's about being a better senior developer day to day. Remember those analogies? They help lock it in.
Definitely. Being able to confidently explain this stuff, debug the compiler errors, pick the right generic approach, that's what sets senior devs apart. You should feel much more equipped now.
So let's leave you with a final thought to chew on. Thinking about legacy code, maybe code you've worked on, how could applying a deeper understanding of generics, maybe refactoring away from raw types, transform those older systems? How would you make them safer, more modern, easier to maintain down the line? Consider the impact you could have.
Great question. Food for thought indeed. If you found this deep dive valuable, please hit that like button, subscribe for more insights like this, and definitely leave us a comment. What was your biggest aha moment from today? Or what other Java topics should we tackle next? Your feedback really helps us shape these deep dives. Thanks for joining us.